these two scenarios. You should have this handout in front of you. Alec travels 240 kilometers in 3 hours at a consistent speed. So we're going to put Alec here, and his distance is 240 kilometers. His time was 3 hours. So that makes the rate what? $80? 240 divided by 3, which is 80 kilometers per hour. Okay, you've got all your little formulas there that you can use to go back and forth if you need to. This isn't really what we're doing. We're just kind of chatting about something, an introduction to this idea. I said it's from grade 9, but immediately there is something that's a twist on the way you look at it in grade 9. So the mathematics is about grade 9 level, like the work, but there's some thinking that's a little bit different. Okay, and then we have Gurpreet. And Gurpreet, you might imagine the first driver, Alec, is taking like a country road. So you can drive consistently at 80 kilometers an hour, not faster, it wouldn't be safe, it wouldn't be allowed, but consistently at 80 kilometers an hour. There's no real traffic or anything like that. So Gurpreet looks like they're taking the 401 and driving 120 kilometers. So 120 kilometers for 1 hour. So that is 120 kilometers per hour. Then they hit traffic and can only go 60 kilometers in 90 minutes. So that would be 60 kilometers in 90 minutes would be 1.5 hours. Obviously, we want to keep things in the same units to make sense of this stuff. So then what would be my kilometers per hour there? 60 divided by 1.5, and I believe that works out to 40 kilometers per hour. And then traveled 120 kilometers per hour. Notice it's giving us the rate for another half hour. So if I put 120 here, and then half an hour, so 0.5. So what would be the distance traveled in that case? 60 kilometers. Thank you. Very good. And we've got that. Now, what's the point of all this? Well, if we're comparing these two trips, here's what somebody might do. If they want to look at sort of the overall average view of Gurpreet's trip, you might do this, 120 plus 40 plus 120. So I added up the three speeds. And how do we take an average? We divide by the number of things we add. So I divide by 3 and I get 93.3. So what would that be? Their average rate. I added up the 3 rates and divided by the number of rates. If you did it that way. Let's take a look at this visually. Here's Alec's trip. You can see why this looks like grade 9. It's a straight line. Just a plain old straight line. The entire trip, Alec was driving. Maybe there was a red light here or there somewhere. I don't know, a stop sign. But the entire trip traveling at 80 kilometers per hour, and in 240 minutes, traveled in 3 hours, got 240 kilometers. Okay, and that works out to 80 kilometers per hour. Okay, but we know Gurpreet had sort of 3 different speeds. So let's take a look at Gurpreet's trip. And remember, we talked about these things. They're kind of called piecewise functions. So this is a function made up of 3 different equations, but it all represents Gurpreet's trip. Okay, and you can see in grade 9, we talk about the steepness of these different lines. So this is steeper. This is where Gurpreet's going 120 kilometers an hour. This is only 40 kilometers per hour. It's less steep. And then this is back to 120 kilometers an hour, but not for as long. Right? And you could talk about each one of these average speeds. But what happens when we want to compare them? So what is that showing us? Adam, what do you think?
The like average speed was the same.
Why do you say that?
Because the like hours both meet at 3 and the distance both meet at 250.
Very good. So this isn't exactly what we're doing today, but there is this underlying important concept in mathematics that you don't take averages of rates by adding them up and dividing by the number of rates. Now, and that's because their timing is different. If the times were all the same, then you could actually do that. But if the times are different, you can't do that. So what we do instead is we add up the total distances. So 120 and 60 is 240. And we add up the total time. So that's 1, 2.5 plus 0.5 is 3. And then we divide the total distance by the total time. This is what we're actually interested in. And again, it does work out to 180 kilometers per hour. So in grade 9, you would look at each of those lines individually and think about their slope, and that would maybe be the end of it. You remember you draw those graphs where you're like, Billy goes to the store and stops to talk to his friend and realizes he's late and runs home, right? And it's the same stupid story every single time, right? And you talk about those graphs, and you would do something with a graph. It would look something like this, I guess. Don't have to copy this down. So going to the store, at the store, running home. And you would calculate the slope of each of those lines and interpret what's happening. Steeper slope means faster rate, whatever the rate is, and sort of direction is like, is it a negative slope or a positive slope, talks about direction. Okay, and then no slope means they're not moving. But you never did anything like this. You never found the slope of that line. Why would you? I don't know. But no. But this is something that we can do, and you'll see that it is something we will do in other situations. What if we want to find the average rate of change between 2 points that are not on a straight line? So in other words, if all I care is the overall average speed of the trip, so how long is it going to take me to get there? These two people had the same trip. The average rate ignores everything that happens inside. But maybe your car doesn't go 120 kilometers an hour. So maybe to you, it matters. Like, I don't know. But the point is, average rate of change, in grade 9, it's all on a single straight line. If I have broken line or a curve, and I take 2 points somewhere along the way that are not connected by a straight line, but I connect them and I find the average between them, I'm ignoring the story of what happens in the middle and just finding the average rate of change. But the math is the same. It's the same formula from grade 9. Finding the slope of a line. That's all there is to it. Okay? We're doing one extra little thing today, but basically it's all based on the slope formula from grade 9. So that's the general idea of what we're thinking about today is, okay, in grade 9 we find slopes of straight lines, but can't I pick any 2 points along Gurpreet's trip and calculate the slope of that line and see what that would represent the average rate just between those 2 points? And that's what we're doing today, is average rate of change. But again, I said this already, that tomorrow we take this an important extra step and we move beyond an average rate of change and we start calculating a different kind of rate of change. And it's kind of a big deal, like I said. And it's important to always remember it's related and built off what you did in grade 9, which was an average rate of change. Okay, and there's a few different types in the practice today that we're going to do. One of them is if you're given data, you're given a table of values like this, how do you find the average rate of change? So here we go. So this one's giving us a rate of change from 2 to 4. So here's 2 and here's 4. And if you remember, H is like my y, t is like my x, and it's delta y over delta x, or delta h over delta t. Delta stands for what? Change. So the change in the h values over the change in the t values. So this is just going to be 380 minus 320 over 4 minus 2. Simple stuff. Notice that 380 and 4 is one of the points, and 320 and 2 is the other point. I can't crisscross those. Right? I got to have a one point, start with the same point. Like usually it's y2 minus y1 over x2 minus x1. You could flip them as long as you flip them both. Yeah. Okay, so this works out to 60 over 2, which is 30. Okay, go ahead and do the other two. And when you're done that, we're going to talk about those answers in a minute. They are going to come back up again. We'll talk about them. Oh, before I move on, sorry, I want to say, so again, look, I started with 80 here. So I started with 14. Like it has to be 80 and 14 and 220 and 12 on top of each other. That's what I mean by order. If you do it in the other order, you'll get the same answer, but you can't flip one and not the other. I hope you understand what I mean by that. And you can see, we'll talk about this in a minute, there's an important thing that happens in the answer that if you always just did the biggest minus the smallest, you'd make a mistake and you'd get the wrong answer. Okay, and that important outcome is very significant. So go ahead and graph these points. Just plot them there on the graph. Okay, we got that okay? So now what I want to do is I want to take a look at all three of these values. So from 2 to 4 was an increase, was a rate of change of 30. So from 2 to 4, and this is a little bit tricky to show, but goes like this. And you can see that, again, it was curved between those 2 points. So the parabolic curve, the function, is not on top of the slope that we calculated there. I mean, it's above it graphically, but it's not the same line. So there's a curve happening. The average rate of change ignores that, and all it does is calculate the change between those 2 points, the ratio of the vertical to the horizontal change between those 2 points. But it's still just slope from grade 9. The next one was from 14 to 12. So what do we notice that's different about this one? It's steeper. That was a big deal from grade 9. What happens when it's the steepest? It's the greatest rate of change. So this is a rocket being fired off a cliff or something like that. So the rate of change does have to do with speed. It's a change in height over time. So this is a faster change in height over time. What else is significant about it? Very good. So that's the connection that, I mean, it's, again, simple idea, I know, but the mathematics, when we did it properly, it worked out to negative 70, and that tells us something. It tells us the rocket's going down. Okay? And then, interesting, I think, the last one is 0. Now look what happens. It's not like there was no change between those 2 times. Between 4 seconds and 8 seconds, there was a change. It went up and came back down, but the average change in height was 0 in that time. That's all that matters, is the average. Does that make sense? But there was no change in height because we happened to pick 2 times where it was at the same height. Any questions about that? Okay, so if you are given data, obviously you just use the table to come up with the points to get your x values and your y values, or whatever the variable is, and use the slope formula from grade 9. If you were given a graph, you would do the same thing. You just pick the data from the points in the graph and calculate the rate of change based on that. Okay, there's a whole bunch of things we're kind of lumping into today. It all has to do with average rates of change. What if you're just given a function? So you don't have this. I know you don't have this, but you can write this one. Find the average rate of change for the function f at x. Looks like it's a quadratic over each interval. Do you remember interval notation? We talked about this a little bit near the beginning of the course. Did some work with interval notation. If you want to remember, the square bracket means include the points, but I don't know how you wouldn't for this. You'd have to. But that is what the notation means. But it's just a simple way of writing from 2 to 5, what is the average rate of change? Again, this is a quadratic, so it's a parabola, so it's a curve. And I'll remind you, in grade 9, all the rates of change that you did were all on straight lines. So it does become, there is a subtle maybe, but a different element to it, a different perspective when we're talking about 2 points on a curve. So delta f over delta x is going to be f at x2 minus f at x1 over x2 minus x1. Using function notation instead of y's is all I've done there. That's like y2 minus y1. F at x2 is your y2 value, right? So this is just the slope formula from grade 9. So in order to do this work, I hope you're keeping up with me here, we have to figure out what f at 2 and f at 5 are. So let's go ahead and do that. 4 minus 4 plus 5 is 5. 25 minus 10 plus 5 is 20. f of 5 works out to 20. Are we okay with this? So then I just do 20 minus 5 over 5 minus 2. Again, just being careful that I'm keeping the order straight. So the average rate of change over that interval was 5. Okay, you can try the next one. Okay, what do you think? Easy enough? I got 2.5 for that one. Nothing fancy, pretty straightforward. You're maybe wondering why we're doing this. It will become more apparent as we get further into this. Yes, it's the same formula from grade 9, but I'll continue to remind you, we're doing it on curves now. So it is a little bit different. And we're going to talk very briefly at the very end about how you might see different examples of this that might be relevant or interesting, or you could see how this is something that people would do. Okay? Okay, but there's another part to it as well. You don't necessarily have to write all of this down because we're going to kind of see it again tomorrow. But you can write down the formula. And the fact that this is called the difference quotient. So the difference quotient is this formula, which is the one we were just using, but we're going to use it in a special way where we're going to use it to determine an expression for the average rate of change between any 2 points on a function. Every function would have a different expression. Actually, not every, but. So this formula is the difference quotient for f at x, some function, over the interval from x to a. We had just did it from 2 to 5 and from 2 to 2.5. What if I just do it from x to a? So f at x minus f at a over x minus a. And graphically, whoops, I didn't leave enough space here to write all of this down. Graphically, is everybody okay? Are we following this all right? You got the formula at least written down, difference quotient? Graphically, the average rate of change is the slope of the secant line. Again, we're going to write this down again more formally either tomorrow or the next day. But what's that word from? Secant. Good. Yeah, good review for the exam, right? Because we got to remember trig from the beginning of the year. Secant's from trigonometry. And remember in grade 10 when you first start learning trigonometry, it's all triangles. And then you get to grade 11 and all of a sudden you're like graphing and it's about circles. And you're like, wait a minute, I thought trig was about triangles. Turns out there's even more to trig than just those things. And it's going to pop up when we talk about polynomials and all of this rates of change stuff. We talk about secant lines. So a secant, this is just another definition. The average rate of change is the slope of a secant line passing through 2 points. So a secant line is a line that cuts a curve in 2 places. So if I have a curve like this, a secant goes like this, cuts it in 2 places. That's a secant line, and I could find the average rate of change between those 2 points. And this is interesting because it goes this, it's negative here, it's going down, it's decreasing, and it's increasing here, but overall it's gone up. What if this was some business or a stock and you lost some money, but overall you've gained money? Right? So this is the kind of thinking that people certainly go through. Well, yeah, the stocks dropped pretty drastically recently, but overall they're still increasing on whatever interval it is you're talking about. Okay, so here we go. This is the last kind of example we're going to do today. Determine the difference quotient for each of the following. Use it to determine the AROC, the average rate of change, for the given interval. So there's my function. Okay, so you want to write this down. This is f at x equals 5x plus 2. So what's f at a? This is a tough question. Nope. That would be f at 0. No? No. It's 5a plus 2. Right? It's just function notation, folks. Okay, so then if we are going to use the difference quotient to find delta f over delta x, this is a little bit confusing for some people because we're using x in 2 different ways here, sort of. Like I could have done f at a and f at b, but there's a reason why we use x, so go with me. If we had used f at a and f at b, you might have been able to follow a little bit more. It'd be 5a plus 2 and 5b plus 2, 2 different expressions, where a and b are any values. But we're using x and a instead because that's our standard. So remember, it's f at x minus f at a over x minus a. That was the difference quotient, that formula we just did. So this is 5x plus 2 minus, careful of brackets, 5a plus 2 over x minus a. But we want to simplify this expression. This is not meant to be hard, by the way, either. This is supposed to be easy. You'll get used to doing this. And the algebra today here is not all that tricky. Are we okay with what I've done so far? It's the same formula from grade 9, but we've stuck with variables instead of subbing in and evaluating. Up here, I subbed in to find f at 2 and find f at 5. Got numbers for those and subbed those in here. y2 minus y1 over x2 minus x1. I've done the same thing here with function notation. F at x minus f at a over x minus a, where x and a are 2 different points or values. Two minus 2 is 0. I get 5x minus 5a over x minus a. What do you think I do now? Nice, common factor, I like it. And then what happens And folks, this is key. We'll talk about this more and more, but that has to happen. Okay? This is what you're working towards. That you get an x minus a factor on top that divides with the x minus a that will always be on the bottom. And what am I left with? 5. Well, what in the world, what is this telling us? That's your average rate of change for what? The whole function. Can you explain that in more detail? Why is that the case? Okay, you're right. Who can tell me why? Well, the function, which we just subbed a into the function, right? So it's the same thing. That's the slope of that function. You pick any 2 points on that line. That's a straight line. 5x plus 2 is a straight line. Pick any 2 points on that line, and the average rate of change between them is going to be 5, because that's the slope of the line. So of course it makes sense that we would have got that. We just proved, using the difference quotient, that the average rate of change of the slope of any line will be consistent for the entire line. Like, we proved it kind of a roundabout way, obviously, but Adam.
So the 0 and the 10, that's just the difference between those 2 points.
So if I had found, I could have also done this. F at 0 and figure it out. F at 10 and figure it out. That's easy, so let's do it. So that's 2, and that's 52. And then if I had done the thing, I would get 52 minus 2 over 10 minus 0, which is 50 over 10, which is 5. So I would have calculated it that way, yes. There's a reason why we're doing it the more complicated way. In this case, it doesn't seem to make sense because it's just straight line. We could have just read it off from the slope, but there's a reason. Okay, and so now what we're supposed to do, which is trivial in this case, it doesn't really make any sense, but in the next example you'll see why we do it. If we were to use this expression to find the average rate of change between those 2 points, I would just say, therefore, the average rate of change from 0 to 10 is 5, because it's always going to be 5. That's what we proved.
Sorry, what is 0 and 10 represent?
That was the interval I chose to calculate.
Is that a point?
No, it's an interval. Five x plus 2 would look like this. 5x plus 2 would look like this. If this is 10, this is 0, that's 2, that's 52, and it would have been from this point to this point, the average rate of change. But it's a straight line, so it's always going to be 5, right? I just chose, like 0 to 10 is just the interval I made up for the question. We good? Next one's going to get a bit more interesting. One more. So we're going to find an expression for the average rate of change between any 2 points, and it won't be as trivial this time, I guarantee. And then we're going to use it to actually calculate the average rate of change from 2 to 4. Are we okay with this? So we've got f at x and we've got f at a. So it's f at x minus f at a over x minus a. So that's the setup. See how that works? Now I could stop here, and technically this would work for what we're doing today. But it's not very helpful. We haven't simplified anything, so it would be the same as doing all the work as we were doing it previously. The reason why this is useful, let's say I need to find like 5 rates of change for the same function, like 5 different intervals. It's better to come up with an expression and then you can calculate all 5 really easily. You'll see that in a moment. So sort of this would work, but it's not really done. And starting tomorrow, 100%, we have to work to pull out that x minus a factor. So we're going to do that. Does anybody know how we might be able to fix this one up to work it out? You can do factor by grouping in a bit of a strange way. Very good. So I'm going to put x. I wonder if you could even do it. You probably could even do it the way that it's set up like this, but I'm going to do it this way, because I think it's interesting. But if you had factored out an x and then factored out an a, that would have worked as well. Yeah. Yep.
You also do difference of squares?
That's what we're going to do. Exactly. So this is a difference of squares. X squared minus a squared. So I'm going to factor the first 2, and I'm going to factor the second 2. That's how we're doing a factor by grouping. But when I factor the first 2, I factor it as a difference of squares, which is interesting. So it's x plus a, x minus a, and that was useful, wasn't it? Plus 3 times x minus a. And now I have x minus a bracket in both parts. So I can pull that out. And I'm left with x plus a plus 3. Yep.
Sorry, what did x plus a?
That's when you do factor by grouping. If I factor out the x minus a, and I'm left with x plus a plus 3 is like my other bracket. Does that make sense? So that's our simplified expression. That's what we were shooting for.
Wait, so like, is there ever going to be a time where you can't, like, where we won't have the points, like, to
Yeah,
work?
sure. And you'd be done here.
Because can't we just solve it to get the same answer just by using the points?
Yeah, absolutely, you could. But something's coming that will complicate things. But like I said, what if for some reason you had to do it 5 times? It'd be faster to do this once, because now when I find the average rate of change from from 2 to 4, I just go 2 plus 4 plus 3, which is 9. Done. And if I had to do that even 3 times or 4 times, maybe easier to do it this way than all that other work. But it turns out the algebra is also, this is like our first step into some important algebra that we're going to need moving forward. Any questions? Other questions about that? Okay, so before we finish, I just want you to take a look up here. And sometimes you need to do this. Sometimes, we forget that there's actually a point to all of this, and we get caught up in the math and the algebra and the skills that are involved. But remember, like, this is all based on modeling of real world stuff. So imagine, when would you actually use this, or when does this become important? Now, these are both straight lines, so they're not as interesting. But what would the average rate of change be for the first graph? If it's change in distance over change in time, what is that? We just looked at an example of that. Speed. Okay, so the average rate of change is speed. In the case of graph 1 here, this is speed. What is this one, my physics people? Acceleration. Very good. If you didn't get that, I would say it looks like speed is increasing. What does it mean if speed is increasing or speed is changing? That's acceleration, deceleration. So this is acceleration. That's easy stuff for those of you that take physics. You're used to that idea. And so average rates of change can represent all kinds of different things, depending on what your vertical axis and your horizontal axis are. So what about this? What does this graph represent? And what would the average rate of change between any 2 points on the graph represent? And this is where I suppose things start to get a little bit more interesting and important. Because if I was somebody that, I don't know, had an agenda that I wanted to, like I was a politician, maybe not a very honest one, and I can't think of anybody right now that might fit this profile, but, you know, and I wanted to like try to prove to people something, I could say, well, look at this. Doesn't look to me like we have a problem with global warming. Because between those 2 points, you know, the planet got cooler. So I think we're good. No. I don't know who you're talking about. No, not necessarily. It's a bit more complicated than that. But it is interesting that if you cherry pick different data points, you can miss the boat of the entire point of, in the long term, from start to finish, look at how it's skyrocketing. And that's maybe more interesting. And this is just an interesting graph in and of itself. So I'll let you think about that a little bit more. What does this graph actually represent? What would the average rate of change represent? But it's got 2 parts to it. It's got these blue lines that are really jumping up and down, because that's yearly average temperature. So the black dots are the average for a year, and the blue lines are connecting the black dots. But then the red line is made up of the average over the course of like 11 years. And so it's not as jarring, and it gives you a bit more of a sense of the overall sort of 10-year rolling average is what that is. And you can see how it does jump around year to year. And I remember seeing an interesting comment on the internet the other day. It was some politician that will remain nameless who was saying about how, you know, we had like a really hot day in December or something like that. And some like 10-year-old replied and said, even I know the difference between the weather and climate. Right? The weather changes day to day and even changes from year to year. But the change in the overall climate of an entire planet, most people think something's actually happening with it.